Well, thank you for coming. Jeffrey Yao, I'm the Chief Data Scientist for an investment management company called AllianceBernstein. I'm also a lecturer at UC Berkeley Master of Information Data Science program. So what we'll be talking about today is the following. So first of all, I'm hoping that in this very quick introductory time series lecture, you will have at least learned by the end of the lecture the characteristics of the time series forecasting problem, how to set up a time series forecasting problem, and the basic intuition of two of the most popular models, one in statistics and another one in machine learning these days. How to implement this in Python seems like a lot to cover, and the advantages and the disadvantages of these kind of approaches. So the agenda is like the following. So first is I want to motivate of a time series forecasting problem, introducing some notations and talk about some of the characteristics. Then we'll dive into univariate and multivariate time series forecasting approaches. And specifically, I will talk about vector autoregressive model in the statistical literature and recurrent neural network. In both of those, I will talk about the formulation as well as Python implementation. Lastly, I want to compare the two methods, and I will conclude with a few words about what are the considerations that you need to have if you want to implement all this in Spark. Okay. So what I did not cover in this introductory lecture, because previously when I covered this, some people say, oh, you should actually put this in a state space representation, which is true. But then the notation will be a lot more involved, and in 30 minutes or even a 90 minutes, it will not be sufficient to cover that. Second is that I won't talk about Kalman filter. Even though the var is actually really, really popular to implement in the form of Kalman filter, I won't be able to talk about that. There are numerous variations of var as well as LSTM. I will only give you the intuition of both of those in terms of the basic structure and the advanced properties of LSTM. Okay. So let's dive into it. So why multivariate time series analysis? Is multivariate time series analysis, which is as opposed to univariate time series analysis, is because there are many time series that you actually need to model them jointly. So one such example is daily interest rate term structure. So interest rate, we may think that there is only one number every day, right? When in fact, I work in the finance industry, every day you actually observe multiple interest rates. And over time, it's actually a curve. So for this kind of time series, you actually want to model them in a simultaneous equations, in a simultaneous system of equations. So, but before we dive into that, let's talk about just the formulation of the problem, right? So forecasting is nothing more than predicting the future values of the series using current information set. Well, specifically, current information set consists of everything that you can observe up to this point in time of the own series as well as something called exogenous series, meaning series that are not determined within the system. Time series problem forecasting require a model, right? So this notation I'll be using throughout the talk today, which is the forecast will denote the forecast as the y hat as a function up to today informations predicting some future. So future meaning period t plus some other periods, for example, period up to h. Right. So the forecast horizon in this particular setup is h. The F here represents some sort of statistical model or machine learning model. It can be actually very simple. It can be very sophisticated as well. But the important thing is that we try to relay current informations to the future information using some sort of functions or some sort of equations. Okay. In math, so the current series or the own series is represented by y sub t all the way to y sub 1, as well as I use bold letter to represent the exogenous series, the xt minus 1, xt, and all the way to the first period that you can observe the informations. Okay. So the information set that we will be using, the notation is denoted as the capital omega. as of time t. It's very important that we fix the time horizon when you do the forecasting. But what models, right? So models actually can be as simple as a naive, just rule-based forecasting, such as tomorrow is just same as today. From notation-wise, the forecast would be then the yt plus 1, meaning the forecast horizon 1 is equal to the current value. And the information set, as you see in this very, very simple rule, is just one data point, which is the data point that you observe up to today. Right? It really can be as simple as today. Once you have that in mind, well, then actually everything, I think, would be slightly easier to follow. So, of course, we can have a model that is more sophisticated than what we just have. Right? So instead of using just the current period, you can have information that use all of the previous periods, such as a rolling average model. The reason I use the term rolling average is that when I teach time series analysis, some people may confuse moving average as the moving average in autoregressive integrated moving average model. So here I purposely rolling average, which is nothing more than a simple equally weighted average of the past k period. Right? So in this case, time forecast horizon is still 1. The information set that you have is to utilize the last k period of the same series of the information set. But of course, this is just a setup, right? We want to talk about models that are much more sophisticated than that, that can utilize information set that are much more efficiently. So before we talk about multivariate time series, let's talk about univariate time series analysis, right? Univariate time series analysis, at least in the statistical literature, is to use the series past value to predict the future. So again, the values from its own series. And potentially, it could also have exogenous series as well, right? But the important thing is that we are only interested in the dynamic evolutions of the series yt plus 1, yt plus 2, etc., using the information that you observe up to time t. Right? One such popular model is autoregressive moving average model. The class of autoregressive moving average model is highly parameterized. In fact, it is a linear function of its own values up to period t, as well as the shocks up to period q. Okay? And again, it models only the dynamics of the series itself. Okay? I obviously won't have enough time to go over that, but if you want all the Jupyter notebooks and a much longer overview of that model, you can look at my PyData tutorial in San Francisco 2 years ago. And I no longer give that tutorial. In terms of the multivariate time series modeling, so previously you saw one equations, but when it comes to multivariate time series modeling, there are actually k equations. And each of the equations is a function of the legs of all the other equations, of all the other series. So as an example, here the setup is it is a function of the p legs of all of the k series itself, right? As well as leg 1 of the k series, leg p of the k series, as well as the exogenous series. So you can think of that the series itself also affected by its own path, as well as the path of all the other series. Not just most recent paths, but the paths can up to the lag p periods. Okay? And that's how it denotes that. Okay. So this kind of setup allows us to model the dynamic of each of the series itself, as well as the interdependency among the series. So let's go back to the original graph that I showed you, the term structure of interest rate, many of those. Right? So you can model the interdependency of each of the series together, okay, in a system. So in what follow, I'm going to use a specific example using 2 series that you can actually download from public website. One is the you see UMC Cent, is the U of Michigan sentiment series represented in green. The blue one is national alcohol consumption, beer consumptions in the United States. The characteristics of that series is that if you have done time series analysis before, the structure, the trend, the pattern of that series is actually represent many other kind of consumption series, even though I use beer consumption. But if you look at other consumptions, almost always look like that. First of all, it is trending up over time for the last 25 years. It has very strong seasonality, right? You see that, right? It spikes up in certain time of the year, every year. And the variance also increasing as well. Okay. So for VAR, in particular, vector autoregressive model, which is a generalization of the AR model itself, it consists of a system of K equations. It applies only to stationary series. I won't give a formal definition of stationarity, but stationarity here really means that the mean of each of the series don't change over time. The variance of the series don't change over time as well. And the variance covariance matrix only depends on the time lag and not the time itself. Okay? That's what stationarity means in this particular context. Now, non-stationary series can actually, in many cases, can easily be transformed into a stationary ones using simple differencing. Okay? When you do that, and the series is not co-integrated, then we can actually apply VAR indifference, and you can still implement VAR. So let's look at VAR more specifically. So let's build it up slowly. So look at, because we have K series, so let's consider the first series as y1 sub t, which is a function of its own path and the shock, right? The own path is denoted as y1 t minus 1. And then you have another series, y2t, which is also a function of its own path, y2 t minus 2, and then all the way to yk. Right? Each one of the series itself is also a function of its own path. But on top of that, you can have y1, which is also functions of y2t. Right? So y1t not only is a function of its own path, but it's also a function of the y2t path. And the y2t obviously affects itself, as well as the K series. Okay? So in fact, in general, you'll get a system of equation like that. This is the simplest case of a VAR model of order 1. Each of the series affected by its own path, as well as the path of all the other series. Okay? Again, to recap, if you look at only the K series, that's the easiest way to remember. A general K is that it has its own path here, as well as the path of all the other series. Okay? Now, the general step to build VAR is the following, and I will only focus on a few steps here. After you split up the series, you actually have to conduct quite extensively exploratory data analysis. And you have to determine whether or not the series is stationary, and then transform the series if it is not. That's 3 steps. Steps 3 to 5 is iterative. Okay? You may transform the series, and the series still may not be stationary. You have to do it again. Do it until you can get a stationary series, if possible. Then you build a model. You do model diagnostic, because all of the statistical model have very strong assumptions underneath that. So you have to do model diagnostic to make sure that the assumptions are satisfied. Then you select your model. You conduct forecast. And then you have to inverse, transform your forecast, and then evaluate your model. So EDA, exploratory data analysis, any time series analysis, we actually should at least plot and take a look at the graph. It may sound trivial to you, but many people, even when using time series, they actually just plot the density instead of the time series graph itself. Second is that time series modeling, we care a lot about the dependency over time. And so one such graph that can capture the dynamic in the form of correlation, the octocorrelation, is the octocorrelation graph, which is the one that is below. Each one bar here represents the octocorrelation between the series and its own path, right? So yt and yt minus 1, yt and yt minus 2, et cetera, et cetera. On top of that, in order to identify the order of an ARIMA model, in this case VAR, you also need the partial octocorrelation as well. And doesn't hurt to also plot the histogram, but that is not the first one that you will look at. Okay. So typically, if you want to implement that, it would be useful to summarize all of those in functions so that every time you run through a series, you can plot many, many of those. Remember, this step is iterative, so it will be useful if you have a function to do that. So the series, obviously, is not stationary, as you see, because when it trends, it tends to go up. When it comes down, it tends to come back down. And so you have to apply some sort of transformation to make the series stationary. So the transformation that is very, very popular to use is first take the log and then take the differences. The difference can be just one step, as well as at the seasonal time period, in this case, period 12. It's useful to write it down because later on, we actually have to reverse transform the series back to its original unit so that it can be evaluate a model. So for the series that I have, for the U of Michigan series, I will take the first difference. And for the BS series, I will take the seasonal differencing. Okay. It is just the habit that I myself like to have. Everything that I calculate, I like to write down what exactly that I'm calculating. And so in terms of autocorrelation functions, it's worth reminding yourself what are the autocorrelation functions look like. Okay. Now, when you do the transformation in Python, it's actually pretty easy. In fact, one step, you can apply the log as well as the differencing to implement the transformation. Now, after you transform, because it's, for example, take at least one period, and in my beer consumption series, it takes 12 periods to do the transformation, you get missing value, right? Because it takes 12 observations to do the transformation. And so it's always worth taking a look at your data or your data frame after you do the transformations, just to make sure that you don't miss anything. Okay. After you do the transformation, like I said, you have to redo the EDA. Remember, this is an iterative process, and so let's just quickly do it again. Once you determine that you have a stationary series, then you propose a model. At the minimum, when you propose a model, you actually have to ask, well, is this model suitable to answer the questions that I have? So for example, what is the dynamic properties of the series? Well, it can be answered by its own lag. What about this other series interact? How can I model the interdependency of the series? You can see that it can be captured by the cross series lag coefficients. Okay. Now, in particular, I have two series, and I propose 3 lags, right? So you have the own lag coefficients in each of the series itself, and then you also have the cross-series correlations to capture the interdependencies. Okay. So at least this model seems to be able to answer the questions that we have. So to implement the model in terms of estimation, the nice thing about Python, in this case, I use the stat models, is that it actually have a very nice functions that you can apply directly to the series that you have. And the only thing you really need to do here is to specify the order. Remember, in the previous equations, I have 3 lags, right? So it's all var model of order 3. And you apply the fit function, which the syntax is very much similar to scikit-learn. And so you apply the fit functions, and you save it in a model object, and then you print all the results. The result is very extensive. It includes all of the statistics that you need to evaluate the model. It also tells you which series that you estimate, et cetera, et cetera. All the coefficients are also listed in your model as well. This toy example is really small, so I only have 2 series and 3 lags, so I can print everything on one slide. But as you can imagine, if you have, let's say, if you have 20 series, 20, let's say, sales series corresponding to each of the stores that you have in your company, let's just say, and you have 5 lags, well, all of a sudden, you take pages to just print out the result. Variance, covariance matrix also come with it as well. And after that, you have to do model diagnostic. Model diagnostic is a graphical technique for you to look at the residuals of the statistical model. And in this case, you want to make sure that for each of the series, the residual look more or less like a white noise, meaning IID, normal random variable. Okay? And I plot both of those side by side. Just eyeballing, checking that. There are formal statistical tests to do that. And I don't do it here. Again, for model, after that, you can do the model selections, and you can run through a grid search in terms of the number of order that you have for the var model to search for the best model that can fit the data. We are not done yet, because I model on the transform series, and this, by the way, is one of the concepts keep tripping up students. they thought, well, OK, I'm done. Well, you're not done, because after that, you still have to reverse transform your series back to the original unit. So if you write down exactly what you model, this step actually becomes trivial, because if you write down the math, then in a few lines of algebras, you can get back to the original series. Okay? So, and I did exactly just that. And the model evaluation that I use is root mean squares. And so again, because I wrote down what I need, right, is the exponential to my forecast, and then multiply by the lag itself, right? So when you calculate that, then you'll get something like that. You'll get some numbers, 180. What does it mean, 180? Or 0.2, I don't even know what it means, right? So one of the things is, even after you do the forecast, you reverse transform your forecast, you evaluate the model, you have to put it into the context. What is the context in this case? The context is that I am trying to forecast the future values of the consumer series as well as the beer series, right? So in those 3 months that I have, I left out 3 months when I did the modeling, the numbers are the following, right? So I need to put the loss back into the original unit in order to put this in a context. The beer is actually measured in terms of median. So that is 4.7 billion, 4.5 billion, and $4.4 billion, right? And so if I put that into that context, the percentage error relative to the mean of those 3 rows of each of the column is 0.2% and 3.9%, okay? I have 8 minutes left, and I have to go through LSTM. Normally, this is a 1.5 hour lecture. So, OK, so switch gear a little bit. So we talk about statistical model. Now we want to talk about neural network model. You may think, well, why do I not just model it using a feed-forward network, right? Well, let's take a look. So in feed-forward network, you have the input. Imagine the x's are your input series. And then you have your output series. In this case, I just use a simple notation. No, I only have one output series. And then you have a bunch of hidden layers. Okay? What is the issues with this? Well, the issue is that information does not account for time ordering. I'm doing time series analysis, right? So this, by the way, also applies to random forest, also applies to many other machine learning methods that you have. It does not account for the time dependency. Second is that inputs are processed completely independently. So meaning the series, there are no dependency among each of them. Meaning this particular architecture has no device to keep up the past informations. Okay? No memory built-in. Well, then why don't we use one that has memory built-in, just like recurrent neural network, which is a very, very powerful network. It can retain past information. It can track the state of the world within the system, and update the state of the world as the network moves forward. Okay? So what does it mean? So it means that from the input to the hidden layer to the output, it goes through some sort of hidden layer represented by ht. But on top of that, it actually has the recurrent loop back to the past, meaning the output as of time t is not only a function of the new input, as it is a function as well as the past hidden layer as well. Okay? And it keeps rolling forward like that. Okay? But there is a problem. The problem of a basic recurrent neural network, which is also a problem back 30 years ago, plug deep learning, is that there is a problem called exploding or vanishing gradient. Because when you move through it like that, the training is used backward propagations, meaning you have to multiply the partial derivative many, many, many times. And so if there is no control over the information flow, the gradient will explode or diminished. And so a few years later, a very, very influential paper was published on LSTM. That was 1997. And subsequently, there are numerous developments based on this particular architecture. When you see blog or read books, papers, more often than not, you see a diagram like this. And whenever I see this, I got a headache. Or like this. Okay? So I much rather to explain it with my own terminology. Hopefully, it's easier to understand. You want to go from one hidden unit through the terminology here is the memory cell to another hidden unit, okay? And through some sort of functions. So meaning ht will be a function of two things. One is the memory cell itself, Another one is some functions that try to regulate how much memory will go into the next stage. That is the key to control the information flow. And so whenever you see GT here, this is called a gate in this literature. So the gate is a sigmoid function. Sigmoid function is bounded between 0 and 1. So 1 means all the information goes through, and 0 means none of the information goes through. So this allows a mechanism to control the path informations. Okay? And as you can see, that within the sigmoid function, it is a function of the path hidden unit as well as the input. Okay? You have the current memory cell, which itself is a function of the past memory cell as well as a candidate memory cell denoted by C tilde T. Regulated by the forget gate, so how much you want to forget about the past memory, as well as an input gate, how much information you want to let in by the new set of informations. So all of these are trained using backward propagation through times. So in summary, LSTM is governed by 6 equations. Okay? These are the 6 equations. Okay. You can implement that in Keras. The underneath of this is TensorFlow. In terms of the step to implement it, you have to formulate the series, scale the series, split the series for training, development, and testing. The important thing is you actually have to reshape the series for LSTM training. And you define the architecture, produce the forecast, and calculate the losses. Okay. So let's continue with the example that I have. In terms of training of the series, it's actually pretty easy to use with the help of Keras, meaning you load in the libraries, the layers that you need, and designing the architecture. Actually, I use a stacked LSTM with 2 hidden layers and 1 output layer. And it can be just as easy as 4 lines of code to specify that. Of course, you have to do some experiment. And then you have to compile the model. One of the things that is different between LSTM and VAR model is that you have to specify the loss functions as well as the optimization functions to train your model. You specify the training, produce your forecast, inverse scale your forecast, and then you can evaluate your model. So in my case, remember the number that we got before, right? So here is the number. Again, just looking at the number by itself, I have absolutely no idea what it means. So you have to put this back into context. The context here is that, at least in the beer consumption series, actually it does better than the previous VAR model, although the US consumer series is not. It actually does better by more than 2% for the consumptions. Okay, comparison, 2 minutes. So VAR, well, VAR obviously apply to numerical time series. LSTM apply to so many more data structure than just numerical time series. For example, voice sequences, tags, and DNA sequences. Okay. For VAR, it is specified of a system of linear equations. LSTM is layers of nonlinear transformations. VAR requires stationarity requirement. LSTM does not. In fact, I purposely did not transform the series into stationary when I trained my LSTM model. Lastly is for VAR, the data processing and the training is relatively straightforward. The only time you have to spend is the EDA part to make sure that it is stationary. LSTM in terms of data processing is a lot more involved. And the network architecture, design training, hyperparameter tuning is, if you have trained your network before, you know that this step is extremely time consuming. Okay. Implementation in Spark. Okay, so now you may think that is, well, everything that I do, why don't I just translate into Spark, right? Because training probably in previous sessions in this room, you may be convinced that, well, just move whatever you have to Spark, okay? So let's see how it works. So if I do that, right, I can still do a lot of the processing in Spark by writing PySpark and all that. But not so fast, obviously. Well, because ordering of the series matter. In this case, you can't just randomly distribute your computation and processing across. Okay? So you actually have to use libraries that respect the time ordering. Flint is one of such libraries actually developed by a very, very well-known hedge fund, 2 Sigma. They open source some of the capabilities of this series so that you can do a lot of processing in Spark. However, when it comes to training, it's still not there yet, right? And so you still all of those, but what you can do in terms of implementation in Spark is that you can conduct hyperparameter training, and then you can distribute the whole model, I have to emphasize that, across your system, okay? That's all I got, exactly 30 minutes. Thanks.
Thank you, Jeffrey. Any questions from the audience while we get the next presenter mic'd up? And is Daniel Cobran around? Questions?
Hi, thank you for the talk. You managed to compress time. It was really interesting, and I'm worried about the backtesting of how do you evaluate the model? Because usually you'll have to train every sample and then only look ahead at the horizon. This is one question. The second, do you have any tips about how to train for multiple horizons rather than having a model for each horizon?
Oh, yeah. Okay. So the first question is related to how do you validate a model or backtest a model in the context of time series. So typically, you want to do walk-forward validation, right? So you cannot randomly drop number of observations. So you have to validate a model by set up your training example in one part in the past, and then you slowly walk forward and predict the future. So that's one way of how you validate a model. The second question is multiple horizon. In fact, both model can actually do multiple horizon times. It's not just one step. You can do multiple steps. Although the two kind of method will differ in terms of the long-range forecasting. So after a certain time period, it will just give you a flat line equivalent to the mean.